Today we discuss chapter 5 vector fields on surfaces and orientation of the surface. First we have some definitions. Vector field on a surface. A vector field x on an n surface S subset of Rn plus 1 is a function which assigns to each point P in S a vector x of P belongs to Rn plus P at P. Rn plus 1 at P. So that means if you have a surface like this, at each point P we have a vector. The vector field assigns at each point P of the surface a vector in Rn plus 1. Okay. Now we have tangent vector field. If x of P is tangent to S, that means at each point P of P in surface, this function x assigns a vector from the tangent vector field. Okay, so tangent space. Suppose we have a surface like this, and I'll write another vector field here. Suppose you have a surface like this. At each point, that vector field assigns the corresponding tangent vector. Okay? One of the tangent vectors at that point. If such vector field, the x of P is called the tangent vector field. Okay, if x of P is tangent to S, that means the vectors assigned by this x of P belongs to the tangent space. We can say that vector field is tangent vector field. Similarly, this x of P is orthogonal to S. Okay, that means x of P assigns vectors which are orthogonal to the tangent space. Okay, that is x of P belongs to SP perpendicular. For each point P belongs to S. Then that vector field is called normal vector field. So we have three definitions. One is vector field, and next is tangent vector field and normal vector field. So this is the definition for vector field. These are two particular cases of a couple of examples of this vector fields. Now we have some remark. We shall work almost exclusively with functions and vector fields which are smooth. That means we are dealing with only smooth functions. A function g from S to Rk, where S is an n surface in Rn plus 1, is smooth if it is the restriction to S of a smooth function from V to Rk defined on some open set V in Rn plus 1 containing S. So that means in order to define a smooth vector field, we need to consider an open set V which contains our surface. Okay, if this is our surface, then we need to consider an open set containing V, and G from V to R, okay, for Rk is smooth. Then we can say that the restriction of this function to S is also smooth. Or otherwise, the other way around, we can think of a smooth function on S as that smooth function should be a restriction of such functions G. Okay, so this is the idea of a smooth function on a vector on a surface. A vector field x on S is smooth if it is the restriction to S of a smooth vector field defined on some open set containing S. X is smooth if and only if the corresponding mapping function x is smooth. So that means a vector field, in order to say this x is smooth, the corresponding component function x of P should be smooth. Okay, in order to get this x of P is a smooth function on S, we need to get this as the restriction of some smooth function defined on an open set containing this S. Okay, this is the idea of a smooth vector field. Now we have a theorem. Let S be an n surface in Rn plus 1. Let x be a smooth tangent vector field S. Let P belongs to S. Then there exists an open interval I containing 0 and a parameterized curve alpha from I to S such that alpha of 0 equal to P, alpha dot coincides with this vector field, and this B is the maximal integral curve. And beta, this alpha is the maximal integral curve. That means there exists another a parameterized curve with this property beta from I tilde to S is any other parameterized curve in S satisfying 1, 2, we can say that this I tilde is contained in I and beta coincides with this alpha. That means in that sense we can say that this alpha is the maximal integral curve on a surface. We have already discussed an analogous theorem in chapter 2 which asserts there exists a maximum integral curve on a level set. Okay, so this is the corresponding theorem for a surface. Now we can prove this theorem. Since X is a smooth vector field, there exists an open set V containing S and a smooth vector field X on V such that this X of Q, X tilde of Q is equal to X of Q for all Q belongs to S. That means that is the restriction. We can consider that as the restriction of some smooth vector field. Let f from U to R and C belongs to R be such that S equal to f inverse C. That means this f inverse C defines the surface. Then we can assume that this del f q not equal to 0 for all q belongs to S. Let we define W is equal to set of all q belongs to this U and V. Okay, all the points common to this U and V such that del f q not equal to 0. Okay. Then W is an open set containing, you know that U and V are open sets, so intersection is also an open set containing S because this is the domain of that function. U intersection V is the this U is the domain of F with the del F Q not equal to 0. So all these points comes from the surface, and both X tilde and F are defined on W. Okay, because these are all points on the points from U and V, so we can easily define this F and X tilde on W. Now you define a vector field, a new vector field Y in such a way that Y of Q is equal to X tilde of Q minus this part into del F of Q. Okay. Note that Y of Q is equal to X of Q for all Q belongs to S. That is because when Q belongs to S, we can say that this X is a tangent vector field. So this is orthogonal to del F Q. So this will, if Q from that S, you can say that this is zeros, and then Y of Q coincides with X tilde of Q or X of Q when Q belongs to S. And let alpha from I to W be the maximal integral curve of Y through P. We already discussed this theorem in chapter 2. For any vector field, we can get a maximal integral curve alpha. So we consider alpha as the maximal integral curve of this vector field through P. Then alpha actually maps I into S because the derivative of this F composition alpha is always 0 due to this. Okay, del F of alpha of t dot Y of alpha of t is equal to 0. Why this happens? This shows that F composition alpha is a constant with alpha composition F composition alpha of 0 is equal to F of P, because the derivative is 0, therefore this function is a constant function, and at the point 0 we have F of P that is equal to C. So this is F composition alpha of t is equal to C for all t belongs to Y. Being this alpha is an integral curve through of Y through P, alpha of 0 equal to P and alpha dot t is equal to Y of alpha of t, but Y of alpha of t same as X of alpha of t for all t belongs to I. Then 1, 2 are satisfied, and 3 follows from the theorem 2. That means we consider a system of differential equation, and by collecting the solutions of such that system of linear equation, and we will construct that maximal integral curve, collecting all the different solutions of the differential equations, and by taking the union of the domain of those solutions. That is the idea given in chapter 2. Then the same idea, using the same idea, we can say that this alpha is the max, or we can construct a maximal integral curve with these properties. So this completes the proof. Now we have a corollary. If S equal to F inverse C, a surface is n surface in Rn plus 1, where F from U to R is such that del F of Q not equal to 0 for all Q belongs to S, and let X be a smooth vector field on U whose restriction to S is a tangent vector field on S if alpha from I to U is any integral curve of X such that alpha of T naught belongs to S for some T naught belongs to S. Then the whole parameterized curve alpha, okay, that all parameterized alpha of T belongs to that S. This is the idea. This is true for all T belongs to I. So I'll explain the statement of the theorem. And suppose we have a surface like this. This is what we called S equal to F inverse C, and the surface of function from U to R, okay, with the del F Q not equal to 0, and X be a smooth vector field on U whose restriction to S is a tangent vector field. So we define a smooth vector field X. When we restrict this to this S, we can say that this is tangent vector field. At each point we have the tangent vector field. Okay, so this assigns vector from the tangent vector field. This is the vector field X. Vector field X. Then, if alpha from I to U is any integral curve of X, that means if you consider any integral curve through this point, so this is an integral curve, then we can say that sum of this integral curve enters to the surface at some point. We can say that all the portion of that integral curve contained in that S. Okay, so once you consider a surface here, and if alpha is any integral curve of this X, we can define. We are considering this X on an open set V of here I take the domain of the X as V. So we need to consider a vector field at all the points of V. But when you restrict this vector field to S, we can say that that is a tangent vector field at S. Yeah. So otherwise we cannot mention the property of this X as a tangent vector field. When you restrict it to this surface, we can say that all the vectors tangent to this surface. That's a hypothesis of the vector field X. So once you consider a parameterized curve or integral curve of this vector field, integral curve means at every point of that curve, the tangent vector and velocity, the vector assigned by this X and velocity vector of that integral curve should be coincided. So once you consider an integral curve which enters the surface S, then the whole integral curve is contained in this surface S. This is the idea here. So we need to prove that whenever alpha of T naught belongs to S for some T naught, then alpha of T belongs to S for all T belongs to I. For the proof, we start with the contradiction. Suppose alpha of T does not belong to S for some T belongs to T after this T naught. Our assumption is once you consider a surface, here, and this is the alpha. This is the point alpha of T naught. This is alpha of T naught. The T naught belongs to S. So we will prove that alpha of T belongs to this S for all T. Okay, we know that alpha of T naught belongs to S. Now suppose that there is some point alpha of T such that alpha of T does not belong to S. So after this the integral curve passes like this. Then collect those points. That point as alpha of T does not belong to S. So after this T naught, can you, if possible, try to find a point T such that alpha of T does not belong to S. You need to prove that all alpha of T is an element of S. If possible, find such alpha of T does not belong to S. Then what happens? You consider this set of all T belongs to I, T greater than T naught. Okay, and alpha of T does not belong to S. If one such point exists, then collect all such points. There. Then f of alpha of T is equal to C for T naught less than or equal to T less than t1. Okay, so by continuity f of alpha of t1 equal to c. That is because this T1 is the greatest lower bound of the set. So this T1 is expected to be the first point at which this alpha of T1 does not belong to us, if possible. Okay. Anyway, if, then for every point less than T1, we can say that f of this corresponding to this point T, alpha of T is a point on the S. Then f of alpha of T is equal to C. Okay, so if this is the case and f is continuous, then you can apply the continuity. Then f of alpha of t1 is also C. Okay, so we can say that this, if this is the greatest lower bound for the set, then at that point we have f of alpha of t1 is equal to C. Okay, this shows that alpha of t1 belongs to S. Clear? So that is a point on the surface. Now you consider a maximal integral curve at the point alpha of t1, say beta. For beta is the integral curve through alpha of t1 of the restriction of x to s. This is the existence of this beta is obtained from the previous theorem. Then this beta is also an integral curve of x sending 0 to alpha of t1. That means beta of 0 is equal to alpha of t1. Okay, because this is the integral curve through alpha of t1. Okay, so now we have we define a new curve alpha tilde of t as alpha of t plus t naught. We can say that this alpha of t1. So when you consider beta, this beta is the maximal integral curve at alpha of t1. Okay, when you consider this curve, then alpha tilde of 0, that is again this alpha of t1. Okay, so we can say that this alpha tilde of t and beta both are integral curve passing through the same point alpha of t1. But we know that the uniqueness of these two integral curves. So this alpha tilde of 0 coincides, or this alpha tilde and beta coincides in some neighborhood of this t1. Okay, so we can say that this alpha of t can be written as alpha tilde of t minus t1, and this coincides with beta in some neighborhood of t1. So we can get alpha tilde of t minus t1 is equal to beta of t minus t1 belongs to us for all t such that t minus t1 in the common domain, that is some neighborhood of t1. Okay, so this is a contradiction. Okay, because we assume that this t1 is the greatest lower bound for this set. Okay, when you consider a point which is less than this t1, then alpha of t belongs to s. Clear? So this is a contradiction for the fact that alpha of t does not belong to s for values of t arbitrarily close to t1. Hence, alpha of t belongs to s for all t belongs to I. Okay, due to this contradiction, we can say that alpha of t belongs to s for all t belongs to I with t greater than t naught. Then the same, in order to complete the proof, we need to work it out with all the points t less than t naught. If there exists a point t which is less than t naught with alpha of t naught does not belong to us, then the same thing follows, and combining those two, we can say that this alpha of t belongs to s for all t belongs to I.